Okay, let's get started. Thanks for joining us today. Today we're welcoming Marion McKenzie from the University of Virginia in the US. She's going to be talking about differential impacts of subglacial bed conditions on paleo-ice flow and subglacial processes. If you haven't joined us, I'll just go over the format for today's seminar. First, we'll do the welcome and announcements, which is what I'm currently doing. Then I will introduce our speaker, and she will take over and give her talk that'll last about 30 minutes. Then we'll do a moderated Q&A where, for the most part, we will deliver questions asked by you to the speaker. There's also some opportunity to raise your hand and ask a question to yourself if you'd like to. Then there'll be a short break, followed by the after talk tea session with the speaker, which is an opportunity in a more casual setting to talk to the speaker about their work and ask any questions that maybe you didn't get to ask before or that you want to get more in depth with. And don't forget to send your questions to us via chat during the talk at any time. You can send that to the questions PaleoPerks host, which today is Pedro, and he'll queue them up so that we can ask them to the speaker during the Q&A period. We just want to acknowledge one of our funders for this, who is specifically funding this section. That's the Quaternary Research Association, and just really grateful for their support and the support of all of our other funders. Just a few housekeeping things to go over before we get started. PaleoPerks values the participation of everyone interested in the paleosciences. Please remember to abide by our code of conduct during the seminar. You will have had to have signed the code of conduct before you got the ability to access the seminar. Please mute yourself during the duration of the talk. You can ask questions by, again, like sending a question in the chat to our questions at PaleoPerks host, or even by raising your hand during the moderated Q&A session. And we'll unmute you during that. Any technical issues can get sent to the questions host as well. We have closed captions built into Zoom. You can use the CC button to show them and hide them. Please nominate any early career researchers that you think would give a great PaleoPerks talk. We are always looking for more speakers. And so many of our speakers have been brought to our attention by nominations from you guys. There's also a weekly feedback form that will be dropped into the chat. This is mostly demographic information. We just like to kind of understand who's coming to our talks. We would really appreciate that if you can fill it out. You can find that in the chat. Also, we have a different survey that we're currently conducting. It's our 2022 participation feedback survey. We're just trying to understand a little bit better what you, the audience, kind of wants to see from us and how we can better serve you. You can use this QR code. There's also going to be a link in the chat to this survey. Again, we'd really appreciate it if you could fill it out and help us. So today our speaker is Marion McKenzie. She got her bachelor's at Gettysburg College in the US, and she's currently a PhD candidate at the University of Virginia. And Marion, whenever you're ready, you can take over the talk and get started.
All right, thank you.
Thank you.
Okay, thank you for that introduction, and thank you all for being here and having me. I'm very excited to share much of my work from my dissertation with you all today. I focus on process-based understanding of how subglacial bed conditions impact ice flow and subglacial processes by using records from the paleo-geomorphological record. And so I'll be sharing two parts today, but I'll begin with some background. Regions of fast-flowing ice that move between 100 and 1,000 meters per year, also known as ice streams, are primary contributors of ice discharge to the ocean. These conduits of fast-flowing ice, seen in yellow and green colors on this map of Greenland, stabilize further inland ice that is cold-based and makes up the majority of the world's freshwater. So if the conduits of fast-flowing ice begin to break apart, the more stable ice that's further upstream will also begin to contribute to sea level rise. And so it's important to understand what controls there are on the existence of these ice streams and what will cause them to move faster. When looking at a homogeneous bed, so in this model, we have a same bed and a modeled ice sheet on top of it, you get this self-organization of these warm-based ice streams that are homogeneously spatially distributed across the surface. But when we look at what happens in the actual record of ice streams, this is an example of the extinct Laurentide ice sheet, where we have ice streams shown in purple. They're not spatially homogeneous. Instead, there's a control of subglacial topography and lithology on the location and speed of these ice streams. Diving deeper into what types of controls topography and lithology has on these ice systems, we can look at the subglacial elevation. So in this grid on the left, we have bed elevation, where low elevation values are in dark blue and high elevation regions are in brown. If we look at the speed of ice on top of this subglacial bed, regions of fast flowing ice shown in yellow and green correlate with areas of low elevation. This is an indication that low relief regions can cause ice streaming through a process called funneling. As ice moves into low elevation regions, it can become thicker, which can induce pressure-based melting, which induces sliding and meltwater at the bed. Conversely, if we consider topographic barriers or bumps in the subglacial environment, this can introduce frictional resistance to ice flow. The relationship between the bed and overlying ice doesn't have a linear relationship, and instead, these two have a relationship that is difficult to constrain and often changes between ice systems and different glacial factors. When considering the lithology of a bed on which an ice system sits, sedimentary or permeable beds with tills or unconsolidated material will allow for water to infiltrate into the subglacial system. However, if you have a hard or impermeable bed in the form of crystalline bedrock or volcanic bedrock, this can form water films and support ice sliding. So it's important to understand the subglacial environment in order to constrain how much meltwater and in what ways ice systems will be contributing to global sea level rise in the past, present, and the future. Looking at these systems as they interact with their bed today in contemporary regions, they're difficult to get to. It's expensive to do this type of research. And so we're very fortunate that paleo-ice streams have a strong record in the geologic and geomorphic record. This provides an opportunity to constrain topographic and lithologic influences on ice dynamics across these regions. We can look at records in the sedimentary record of what was directly deposited by ice. And so on the right here, there is a record of ice rafted debris deposited in marine sediments and other tills that were deposited along the modern day Washington coast. But today I'm going to be focusing on the geomorphic record, which not only gives a really good understanding of the locations of where ice streaming took place and how retreat happened, but looking at these features and their morphometrics tell a story of how ice moved across the landscape as it interacted with the bed in which it sat. So I'll be zooming into streamlined bed forms, the majority of which were created during the last glacial maximum, which was about 20,000 years ago, when all ice sheets across the globe were at their maximum extent in the Quaternary. However, the timing of when these bed forms were created isn't directly related to my results because I take a process-based understanding to how these streamlined bed forms tell us about ice processes and subglacial dynamics. As ice moves across the landscape, the sedimentary processes at the ice bed interface can form erosional and depositional bed forms that are elongate in the direction of ice flow. Some examples of these are shown in the images below, where whalebacks are erosional features elongate in the direction of ice flow and can be found to be meters long, wide, and high, while megascale glacial lineations and flutes are both depositional bed forms, but range in size. So MSGL are kilometers long and 100 to 1,000 meters wide, while flutes are only meters long and centimeters wide and high. But across all scales, these features can be associated with ice flow speed and warm-based ice. And what I mean by associated with ice-based flow is that if we look at this image on the left, these features are much longer or have a higher elongation ratio, which is a bed form's length to width metric, which indicates that the ice that created these features must have been moving faster than the ice on the right to create bed forms that were much shorter. So the bed forms on the right, which are less elongate, indicate slower flowing ice. Faster flowing ice is on the left with your more elongate features. Perhaps most importantly for this talk, though, streamlined subglacial bed forms are indistinguishable between paleo and contemporary subglacial beds. So if we see subglacial streamlined bed forms created in the Rutford ice stream in modern times and compare them to the Dubont Lake streamlined bed forms, as King et al. 2009 did, these features are morphologically identical, indicating that these processes have been the same through time. Therefore, looking at these bed forms as a proxy for ice streaming and different characteristics is possible and a really useful proxy. And so that's exactly what I propose to do. And what I will show you that I did is using these streamlined bed forms to create a process-based approach and identifying controls on ice stream behavior. I begin by identifying streamlined bed forms across deglaciated landscapes. I correlate quantitative bed form metrics with landscape variations, and I take these results to infer ice flow dynamics of paleo-ice streams across various locations. So in the first part, I'll share 9 sites of paleo-ice streams that I identified across the deglaciated Northern Hemisphere. The first site I'll assess is the Puget Lowland in Washington State, which was glaciated by the Cordilleran ice sheet. Both northwestern Pennsylvania and Chautauqua, New York, were glaciated by the southernmost Laurentide ice sheet. In northern Canada, also glaciated by the Laurentide ice sheet, are sites McClintock Channel, Prince of Wales Island, and Nunavut. I have a site in Bartholomew, Iceland, which has volcanic bedrock and was glaciated by the Icelandic ice sheet. And my Fenno-Scandinavian ice sheet sites are northern Norway and northern Sweden. All of these sites have different styles of ice streaming, as we can start to see in these LiDAR images, where these bumps are our streamlined bed forms, and they range in their size and shape. And so we'll explore in a bit what these differences are quantitatively. First, I'll break down the different sites and what their lithologic and topographic conditions are. So my crystalline and volcanic bedrock sites are Nunavut, Bartholomew, northern Norway, and northern Sweden. Sedimentary bedrock sites are seen in northwestern Pennsylvania, Chautauqua, McClintock Channel, and Prince of Wales Island. And then a unique site that I'll explore later in this talk is the Puget Lowland of Washington State, which has a sedimentary bed with crystalline bedrock and volcanic bedrock interruptions throughout the landscape. Lastly, I classified topographic controls on each of these sites, where a site was either defined to be topographically constrained or in a valley, or topographically unconstrained. So my sites that are in a valley are the Puget Lowland, Bartholomew, northern Norway, and northern Sweden. So as you could see on the previous images, there were a lot of bed forms. So in order to make it easier on myself to map them, I developed a semi-automated tool that utilizes slope variations across the landscape. Topographic Position Index takes a defined neighborhood size and can calculate differences in slope across landscapes to capture different scales of features that we see. An example of how this works, this is Chautauqua. When I utilize the TPI tool, it pretty accurately can identify many of these streamlined bed forms. It does have to undergo a manual assessment, however, and in doing so, I removed, out of the 702 total bed forms, I removed close to 500 and added about 100. For all of my sites combined, I identified over 7,600 bed forms, and then nearly 4,000 were manually mapped, which leaves me with a total of 11,628 bed forms. All of them are mapped here on the right, but if we zoom into 2 of these sites, where C and D are Chautauqua and McClintock Channel, respectively, we can already start to see that the morphometrics of these features are pretty different. And so we're going to quantitatively assess how they differ and why they could be differing based on the topographic and lithologic characteristics of these sites. I'll mention that the colored boxes in this figure will be brought up later to assess spatial distribution of elongation. So just keep this in mind, I'll bring it up again. When looking at the morphometrics of these bedforms, where along the x-axis we have bedform width to the y-axis bedform length, on the right, each point represents a singular bedform identified in this work, colored by the site in which it was identified. And on the left, this is a convex hull outline of where these bedforms exist in the width versus length distribution in order to better see the overlap of the sites. But the most important takeaway here is that there's this minimum width to length ratio in which we see all bedforms across all sites existing. And this is indicating to us that ice streaming affects the bed similarly, regardless of the topography and lithology at the sites. If we assess elongation ratio, which is again the measure of the bedform's length to width, we can see that across all sites, again, regardless of lithology or topography, that the ratio of high elongate bedforms and low elongate bedforms are the same, meaning that the distribution of ice speeds are relatively similar throughout all sites. This has been seen before in the literature. And here I am calling up the boxes I brought up a few slides ago. This is the spatial distribution of elongation across all sites. And so the more elongate bedforms indicated by dark blue at almost all sites are pretty well interspersed with low elongate bedforms indicated by white and light blue. This is the case that streaming is dynamic and we have these formations of bedforms intermixed with one another, but that happens at all sites except for McClintock Channel at D, where we have high streaming or highly elongate bedforms in the center of an ice stream region and less elongate bedforms on the margins, indicating that the margins are probably experiencing more frictional resistance than the innermost high velocity ice flow itself. And so again, we see that elongation profiles are telling us that all sites indicate similar anatomy despite bed characteristics, and more elongate bedforms are interspersed with less elongate features except for that one site. When we think about subglacial processes as it relates to ice flow speed, along my x-axis, we have elongation ratio, and the y-axis indicates bedform surface relief, which is a measure of the highest elevation point along a bedform long axis minus the lowest elevation point along a long axis. When the elongation ratios are high, indicating that the ice that's creating these features is moving quickly, the bedform surface relief is even, meaning that as the ice is creating these bedforms, it's creating an even surface and is eroding or depositing material in an even manner across the landscape. When looking at low elongation ratios, where ice is moving slower to make these features, the bedform surface relief begins to get very large. This is an indication that the subglacial processes are less organized and are not depositing or eroding material in a uniform manner across the landscape. Next, I'll look at the specific topographic and lithologic characteristics of each site and how it relates to bedform surface relief. So again, this is a measure of subglacial processes and their efficiency. And we see that at our topographically constrained sites of Puget Lowland and Bar the Dollar, we have the least efficient subglacial processes as shown by the really high bedform surface reliefs in these violin plots. However, if we look at our sedimentary bed systems that are topographically unconstrained, all of these sites are creating bedforms that have low surface relief, indicating that there is even subglacial processes occurring across the landscape. And this would mean that these types of sites induce organized subglacial flow. So again, subglacial processes are most organized in these unconstrained sedimentary beds, while the topographically constrained hard rock beds are most likely to create bed forms with uneven surfaces. When we look at the elongation ratios correlated with ice speed at each of these sites, we see that at our, again, topographically constrained sites, we have the highest elongation ratios or the fastest moving site ice. This is what we would expect to see based on the ice funneling I mentioned at the very beginning. And when we try and correlate bed lithology to elongation ratio, there isn't any correlation. And this is an indication that topography has a higher order control on ice flow than lithology in ice stream environments. So I've just shown at a multiple location analysis of how subglacial processes in ice flow is sensitive to bed characteristics. And these are some of the findings. So again, topography has that first order control on ice streaming. Lithology is a second order control. Topographic funneling causes an increase in ice velocity. We see ice streaming influences bed similarly, regardless of bed lithology, and elongation are spatially diverse at almost all sites. And faster flow generally correlates with even bed form surface elevation, indicating there's efficient and uniform erosion and depositional processes in the subglacial environment. However, there's one aspect of this that I haven't talked about yet, and that is how topographic highs influence ice behavior and subglacial processes. And so to do so, we're going to zoom into a single system to eradicate any glacial conditions that could impact results from across different ice systems. So if you remember, when I was introducing my sites, I mentioned we would come back to the Puget Lowland, which is a very interesting region that has sedimentary bed with crystalline and volcanic bedrock bumps protruding at the surface across the landscape. And so assessing streamlined bed forms and ice streaming across different hard rock beds or bed bumps provides an opportunity to empirically consider how ice flow persistence and velocity change across these bumps in a single glacial system. So I'm working with 9 bumps in this system. They vary in size from 48 square kilometers to 2 square kilometers. And this figure here is a representation of how these bumps scale to one another in terms of their surface area. So I will pull up this figure in multiple other results slides so that if you forget the order or the magnitude in which these bumps compare to one another, this is what I'm referring to. So these are the mapped 9 sites that I chose, where the largest one is up here is I, and down here is 9. And I identified the outermost 100-foot contour at each of these bump sites and then expanded it 3 times. From modeling, we see that that's about the area that a subglacial bump impacts ice flow. And so we decided that would be the best way to assess the influence of these bumps. From here, I used not only topographic position index, identification of streamlined bed forms, but also a tool called contour tree mapping, which uses elevation differences across the landscape. So this project utilized 2 semi-automated mapping tools. And after all of the bed forms were identified in these site regions, they were separated into 3 groups, either upstream of a bump, on top of a bump, or downstream of a bump. Then these populations were compared not only within each site to assess changes across the bump, but also between sites so that we could assess how the size of the bump impacts ice flow differently. And so based on what I showed in the first part of this work, we would expect that as the ice moves onto these hard bedrock surfaces, that the bed forms it's creating have a higher surface relief because the crystalline bedrock and volcanic bedrock are more difficult to erode than the sedimentary bedrock surrounding it. And that's exactly what we see. So on the surface relief shown in this bottom right figure on the x-axis, these density plots indicate that as ice is moving on top of the bump, the surface relief is generally getting larger and then again becomes smaller as it moves as ice moves downstream of the bump and regains the ability to create bed forms that have an even surface. When we look at elongation ratio across the bumps, the bed forms across the bumps, as ice moves on top of the bump, the elongation ratios of the bed forms become shorter, indicating that ice is slowing down as it moves on top of the bump. So these two density plots are showing us that bumps generally reduce ice flow speed and efficiency of sedimentary processes across all of these sites. And bedform surface relief is lowest downstream of the bumps, indicating efficient sedimentary processes in the downstream environment after ice has gotten past this topographic barrier. Now I'm going to again compare elongation ratio and bedform surface relief, but this time with scatter plots. And I'd first like to walk you through what we would expect if populations show up on different regions of these graphs before showing you the results. So if we have bed forms mapping in the highly elongate area of this map and low bed form surface relief, this would indicate to us that ice is moving quickly and has very efficient subglacial processes, which are creating bed forms that are even across the surface. However, if bed forms are mapping in this upper quadrant of low elongation ratio and high bed form surface relief, we would expect the ice to be moving slowly and to not have efficient subglacial processes developed in that environment. And so the bed forms that are created on top of the bump are seen to move into this quadrant more of low elongation ratio and high bed form surface relief, which is an indication supporting what we saw from those density plots of a decrease in ice speed and efficiency. However, what I'd like to call your attention to as well are these outliers here. So a lot of the outliers in this upper region are dominated by our larger bed bump sites, whereas the lower outliers are dominated by our smaller bed bump sites, which is providing information that the size of the bump does matter in the way that it controls ice streaming in these environments. So to assess this further, I looked at the orientation or cardinal direction of these streamlined bed forms upstream, on top of, and downstream of the bumps. These are just the three largest sites, but as we look at the orientation as shown in these rose plots, as the ice moves on top of the bump, it begins creating bed forms that are much less organized in terms of orientation than they were upstream of the bump, indicating that the bump is disrupting the orientation of flow. However, in the two largest sites, which are greater than 4.5 cubic kilometers, we see that downstream, the ice is able to regain this orientation and organization of the direction of flow. And so while bumps generally lead to ice flow deceleration and reduction of sedimentary process efficiency, as shown in two of the slides before, we also see that sedimentary processes are most organized and efficient downstream of bumps. And this is possibly a result of an introduction of subglacial meltwater from strain heating as the ice moved on top of the bump. So that wraps up my results part of this talk, but I would also like to share some of my ideas on future analysis and application. I've been thinking a lot about including these types of dynamics in modeling of ice flow and subglacial processes. There are some really great scientists that are working on these questions, and so they have been on my mind. And I've also been thinking a lot about incorporating geochronology into bed form formation, especially of bed forms that are created through multiple glacial cycles. And then thinking about correlating glacial feature and bed form mapping to interests in other fields, such as nutrient transport, understanding just different dynamics across fields. So if you have ideas about this or think about glacial features in any way, I would love to chat with you after this as well. I would like to acknowledge that the University of Virginia, which is where I do the majority of my work, is the traditional territory of the Monacan peoples. As ancient peoples who thrive today, I acknowledge and respect their stewardship of the land past, present, and future. Thank you to my advisor, Dr. Lauren Simpkins, and all of my collaborators on this work for their support and contributions. And my internal UVA funding sources are here, as well as my data sources. So with that, I'll say thank you and take any questions.
Thank you. Thank you. That was fantastic. Really great talk. And I appreciate you walking through your conclusions and the way that you did. That was really, really a great talk. Oh, you're welcome. So please feel free to ask questions either through the chat by sending them to our questions host, or just raise your hand and we'd be happy to unmute you and let you ask the questions yourself. So let's see if we have any questions so far. Looks like we do. Hold on a sec. Hold on, I'm just popping this in the chat here. This question is from K. Sender Sarwan. They asked, the diagram of ice velocity on Greenland from Straneo et al. Indicates high velocity at the fringes and the distribution is almost fractal. Are there structural/physical reasons for this?
Would you mind repeating the question? Sorry, I can't see it in the chat.
Sure. It's in reference to a diagram, I think at more towards the beginning of your talk. It says the diagram of ice velocity on Greenland from Straneo et al. 2019 indicates high velocities at the fringes and the distribution is almost fractal. Is there a structural or physical reason for that distribution?
That is a good question. I would think so. A lot of the margins of Greenland have like valley systems. So we discussed that, as like ice moves into a valley, it would speed up. So the topographic underlying topography of Greenland would probably be a good explanation for why you see that trend, but I would definitely suggest checking out that paper.
Cool. Great. And while I'm just waiting for some other questions to get queued up, I was curious, this is all very new to me, so it was learned a lot. But what are some ways that the lithology that you talked about, like what are some reasons that affects this like speed and the way that ice is flowing?
Yeah, so a lot of it has to do with subglacial meltwater and the ways that is able to affect ice. And so if you don't have infiltration of water into the subglacial system, it can create a water film, which you can imagine would cause ice sliding across large surfaces. But if you have sedimentary systems where water can infiltrate into the subsurface, you might have different dynamics occurring in that environment.
Cool. Okay, I see. Awesome. Thank you. Let's see. It looks like there's one here. We'll pop it into the chat. This one is also from K. Center Sarwan. How do bedform and ice sheet behaviors vary across Heinrich stadial and interstadial periods? And how sensitive are these processes to larger climatic processes? And given the currently rapid climate changing conditions, how are these processes likely to change in this respect?
Yeah, so that's another great question and one I've been thinking about a little bit. So a lot of what I do doesn't consider like timing of when these features are made or like the climatic variability in their formation. But I can hypothesize that in periods of warming, we would have greater ice streaming, so greater formation of streamlined bed forms. And this might be better seen in an offshore record. So if we were to correlate onshore geomorphic observations with offshore IRD or deposits from these Heinrich and interstatal periods. That would be a way to kind of test what's happening there.
Cool. Great. Well, let us, well, I'll just hang out a minute or so to see if we have any other questions. Please just raise your hand if you want to ask anything. Also feel free to stick around for tea if you want to ask more involved questions. That's always fun if you want to talk a little bit more about methods and things like that. Okay. Well, great. If there aren't any more questions, I will just do a couple things to close out this portion of the seminar. Let me just share my screen. Okay, thank you so much for joining us for this talk. Please, if you can, fill out the weekly feedback form that's been linked in the chat so we can learn more about who came today. Also, next week. We are taking a little break, so enjoy your break next week. But join us on November 22nd for a talk with Annika Brombacher, who's going to be discussing developmental plasticity in the fossil record, a case study using planktonic foraminifera. And again, we just want to acknowledge one of our funders who specifically supported this event, the Quaternary Research Association. We really appreciate their support, as we do the support of all of our funders. Again, I just want to remind you, we have a participation feedback survey going on that's really going to help us understand how to better serve you, our community, going forward, and different things that you'd like to see us do or that are working for you that maybe aren't working for you. So it'd be really, really helpful if you could fill out this survey. That was also linked in the chat. Up next, we're going to have tea time. That's our fun, informal conversation with the speaker, and kind of a question of the week to kind of get you thinking and prep for tea time is if you could travel to any glacier flow, which one would it be and why? And maybe let's just say any glacier flow ever in time. What would you want to see? So I am going to set this timer. And in 2 minutes, we'll reconvene and start tea time.